But it's not all about stars and galaxies. JWST was also built with a relatively new, exciting field in mind: exoplanets. Planets that are outside of our own solar system. Although there weren't any confirmed exoplanets while Hubble was being designed and built, it has contributed significantly to this emerging field, giving us this first visible light image of one. Now, there are over 5,000 confirmed exoplanets, and in the last few decades, we've learned that the overwhelming majority of stars have planets.
JWST has capability to study exoplanet atmospheres to a degree and precision that has never been done before. And so the infrared part of the spectrum offers a really great insight into some of the really interesting chemicals that might be in a planet's atmosphere. Things like water vapor and carbon dioxide and methane. Things that could possibly signal a surface that is habitable.
And there's one particular system that's on everyone's mind. It's called TRAPPIST-1, and it has multiple planets in the habitable zone, the orbital region around a star in which an Earth-like planet can have liquid water on its surface and possibly support life.
We will be looking about 40 years back in time, which is literally in our backyard. The TRAPPIST-1 system is what we can call the rock star of exoplanet. This is a star that is very small, not much bigger than Jupiter, and that star has not one but 7 planets transiting its star. And we know that these planets are of mass and sizes similar to the Earth, and 3 of them, and maybe 4, are right in the habitable zone. And this system is very close to the Earth, 40 light years away, and this is the one that we'll be looking very hard to find whether these planets have an atmospheres, and you know, if there's a system to point where there's maybe life, that's the one, the TRAPPIST-1 system. The Hubble Space Telescope tried to detect the atmospheres and so far has failed. And we need a very powerful telescope like James Webb to detect the atmosphere, finding whether they have oxygens, water, all the molecules that are required for life as we know on Earth. There are several methods, but the one that will be used very much by James Webb is the transit method. This is by chance, you have a planet that goes in front of its star from our perspective, and you can see a little light dipping as the planet goes in front of the star, and that allows us to measure the radius of the planet, but also we can actually probe the atmosphere. So the light that is filtered by the stars, by measuring the colors of the atmospheres, gives us a lot of information about the atmosphere. It's called transit spectroscopy, and that's a technique that's been used with Hubble, but with some limited performance, and the James Webb Space Telescope will be very well optimized to do these kinds of very delicate observations. And the TRAPPIST-1 system is by far the best system. This is the one that will give us the strongest signal, and there will be lots of time devoted to that system with all science instruments on board the JWST. It is to do with the fact that
there are estimated to be billions of trans-Neptunian objects, even if at this moment we have only discovered around 3,000 of them. TNOs are one of the most pristine bodies in our solar system. That means that they have been not too much processed since they formed. So they hold clues and they hold information from the very first stages of the formation of the solar system. This basically means that they are like frozen time capsules that are there waiting for us to unveil those secrets. The largest objects in the trans-Neptunian belt, together with Pluto, is Haumea, Iris, and Makemake. And because they are so large, they have activity, they may have an atmosphere, they have a lot of ices, like methane, nitrogen, CO. Those are in the largest TNOs, and we think they were an ingredient for the formation of all the TNOs. But when it comes to really know what is on the surface of these objects, we don't really know. The physical and chemical state of these ingredients, the recipe to cook a small body. We have 60 TNOs in our sample. We have representation of all the colors. What we are doing is we take the light that comes from one of these bodies, and then is channeled through this instrument. Is called NIRSPEC, and this is a near-infrared spectrograph. NIRSPEC is going to observe in a part of the light that can't be reached 40 nanometers from the Earth. So we are just separating the light to get to know really each single material that can be there. So James Webb comes on time and is perfect to do this science because it's out of the atmosphere. We have a preconceived idea of what is a TNO based on the knowledge that we have, but our knowledge is limited. And the best things about tools like JWST is that they are really discovery tools. They are going to provide us with many answers to questions that we didn't even know we had.
Apart from JWST, many ground-based telescopes will be coming online in the next few years, complementing the science JWST will do. Like the Vera Rubin Observatory in Chile. It is a wide survey telescope expecting to discover thousands of new objects like TNOs, so then telescopes like JWST can look at them in more detail. And the next big space telescope is just around the corner.
The big telescopes like Hubble and JWST only come along, once every couple of decades. And the next big telescope like this that we're building is the Nancy Grace Roman Space Telescope. So that particular telescope is not quite as big or expensive as JWST, but it is also an infrared telescope that's designed to see the universe in more of a broad sort of swath. So telescopes like Hubble and JWST are designed to see small parts of the universe very deeply. But by looking a little less deep but more wide, we can learn different things about the universe. People often ask, are these telescopes worth it? And we're spending a lot of money on these telescopes. JWST is $10 billion. Hubble, from its inception in the late 70s all the way to now, is about $16 billion. And so the question of is it worth it is an important one. These are funded by taxpayers. And of course, all of that money that's quote unquote sent into space is spent right here on Earth, of course, funding high-tech jobs. But in addition to that, I think if we look at the past 30 years of Hubble and what we foresee as a bright future with JWST, if you put that in the context of, money spent per year, it turns out to be less than a cup of coffee, a cheap cup of coffee per citizen per year.
Human beings are curious. We all want to know from where we come. Yes, we exist because stars exist. Stars are the building block of galaxies. They produce most of the power, the light in the universe. And they also make up the elements. Elements like carbon, oxygen, nitrogen, iron. Most of the elements in our body were actually made up in a star. And in fact, there is more. Some of the heavy elements in our body, like gold, copper, zinc, actually formed when a massive star exploded as supernova. So even though studying how stars form will not tell us who we are as human beings, it will definitely make us understand, make us realize that without stars, we would have never been there in the first place. And so it's good for us to understand what are the elements and the processes that are actually needed for us as human beings to exist.
I know for myself, thinking over the past year, the past couple of years, much negativity, having the positivity of a mission like this to look forward to, and something that's working and successful and is a symbol of people all over the world working together to achieve something that is technologically amazing. For me, that's awe-inspiring and gives me hope for the future of humanity.
Planet Earth and not go and think about these beautiful things that we see. But then on the other hand, it's like, things like understanding how stars work can teach us about nuclear fusion, for example, the way that the elements are produced in the universe. I think it's just a fundamental question that human beings should want to know.
Together, and you ask the question 5-10 years later, what was the main discovery that this telescope made? Nobody could predict it. I can talk to you about all the kind of stuff we think we're going to be doing, but you know what? We don't know. And that's the most exciting part.